Okay, in this video we're going to consider a special type of probability distribution, which is called the binomial probability distribution. This distribution is only applicable if it's made of independent events. Each trial can be classified as a success or a failure. There are a fixed number of trials. It cannot go on forever. And the probability of success on each trial must be constant, right? So let's look at an example real quick. Let's pretend we have a coin, and let's pretend this is a rigged coin. I don't know if you ever come across one of these, but let's pretend when you flip this coin that there is a 30% chance that it will be heads and a 70% chance that it will be tails, right? So we can define success as, in this case, our success would be getting tails, right? So that meets this. Can I classify as success or tails? Yes, our success here is tails, which occurs 70% of the time, right? Is it independent? When I flip a coin, is the next flip independent of the previous flip, right? Yes. Unlike a deck of cards where if I pick out like an ace, then originally there's 52 cards. If I pick out an ace, there's now 51 cards. So the next one, if I don't replace that ace, the next one would be dependent on the first one, right? Coins are independent because, the flips do not influence each other. Is there a fixed number of trials? Yes, let's just say we're going to do 50 trials, right? We're not going to do this forever, but we'll do 50 trials. And then, was the probability of success constant? Yes, we're saying that this, this is always 0.7. It's not going to change whatsoever, right? So in this case, that would be, we could use that as a binomial experiment. So again, it has to have some sort of success, and whatever the probability of success, there's also the probability of failure, right? So in this case, the probability of success is 0.7. The probability of failure is 0.3, right? So in this case, we'd say the probability of success is called P. If you can find the probability of failure by just subtracting 1 minus P, right? So if P is 0.7, then 1 minus 0.7 is 0.3. Which is the probability of failure, right? So it's got to be binomial. It's got to have two things, success or failure. It cannot be anything besides that, success or failure. A lot of times it's just about reworking your view on it. Like, how do I look at this so I can see the success and see the failure in order to actually classify it as a binomial experiment. Okay, so look at a quick example. Let's pretend we have this spinner right here that has 3 blue sides and 1 white side. We're gonna so the probability of landing on blue when you spin this thing would be 3 out of 4 because it's 3 of the 4 sides are blue, and the probability of white would be 1/4. We get to choose. Let's choose success to be blue, right? So I consider success is when I land on blue. The probability of success is 3/4, right? So we're saying the probability of success is 3/4. If I want to find the probability of failure, I can just do 1 minus 3/4, which is 1/4, right? So that's all that says is 1 minus P is the probability of failure. Let's consider we spin this thing 3 times, right? The probability, we could create a tree diagram here, which looks like this. On our first spin, the chance of getting a blue is 3/4. On our second chance, it's still 3/4 for blue and 1/4 for white. And so you could create a tree, a probability tree that looks like this. I hope you've seen that. I hope you at least saw this last year, right? Where you create this tree of like on every single spin what could possibly happen, and then we could create a probability distribution of saying, okay, what happens when X is what's the probability of getting 0 successes? None are blue, right? So you'd look at this and you'd say, which one of these represents none blue? Well, that would be this case down here, right, where you got white, white, white. Right, and the probability that would be 1/4 times 1/4 times 1/4, which is 1/4 of a third. You could then look at this one. What's the probability of getting exactly 1 blue? Right, and you'd look at that here. That would be that's what these check marks are. Right, you got blue, white, white. You have white, blue, white, and you have white, white, blue. So there are 3 of those. So you take that probability of 3/4 times 1/4 times 1/4. Each one of those is 3/4 times 1/4 times 1/4. And you multiply by 3 because there's 3 ways to get that, right? And you do the same thing for each of these, right? And you can then create your probability distribution for all of those, right? And the maximum number of blues you're going to get is 3. So this gives you your probability distribution for success being blue and failure being white. What we're trying to notice here is that For 0 blues, it was just 1/4 to the third, which in terms of combinatorics is just this here, right? And its probability of x getting 1 was 3 times 1/4 squared times 3/4 to the first. And then 2 is 3 times 1/4 to the first. So let me copy this to show you what's actually happening here. Sorry. So just for a second, I want you to consider what this would look like if I added all these together, right? I'd get 1/3 to the third plus 3 times, sorry, 1/4 to the third plus 3 times 1/4 squared times 3/4 to the 1 plus 3 times 1/4 to the first times 3/4 squared plus 3/4 to the third. And I don't know if you recognize what this is, but it has to do with this thing. Pascal's triangle. Notice how, you know, this coefficient, you don't see it there, but it's 1. Then you have 3, 3, 1, right? And then you also notice how this goes 3, 2, 1. And then here you have 3, 2, 1, right? This is basically just the binomial expansion of 1/4 plus 3/4 to the third power. Is it not? It is just that. It's just the binomial expansion. Remember what binomial expansion looks like? That's all this is the expansion of 1/4 plus 3/4 to the third power. So in case you don't remember the binomial theorem, the formula looks like this, which is saying if you're trying to expand a binomial a plus b to the n, ends up looking like this, and the general formula is this thing here, right? N choose r over n, a times n minus r b to the r. In this case, your a is 1/4, your b is 3/4, your n would be the power, which is 3, and your r would be your r is just going to change from 0 to 3 as you go through this thing, right? So just recognizing this probability can be used, it can be seen as binomial distribution, right? And the first term in the binomial distribution gives me the probability that x is 0. The second term gives me the probability that x is 1. And the third term gives me the probability when x is 2. The success of two successes. And the last one gives me the probability of 3 successes, right? So let's look at another example of this. Okay. An archer has a 90% chance of hitting a target with each arrow. 5 arrows are fired. Determine the chance of hitting the target. So we're going to say, in this case, we're going to say success is hitting the target, and the probability of success is 90% chance, right? So that means 1 minus p, the probability of not having success is 10%. And so just like we did up here, where we saw it was success and non-success, or vice versa, we're going to go and write this as 0.9 plus 0.1 to the 5th power. And the reason we're using a 5 here is because we're going to do 5 trials. If we want to do 10 arrows, then we put a 10 in, right? And then we would just go ahead and expand this thing using binomial theorem, which I guess we'll go ahead and do. So we can go ahead and draw our Pascal's triangle if this helps you do it. If it doesn't, then you can use the, right? Hopefully you have your Pascal triangle not memorized, but how to at least get it. We're doing a 5th trial, which means this is whatever to the 0 power. This is squared, 3rd power, 4th power, 5th power, 6th power. We're doing 5th power, so we're going to use this. Those are going to be our coefficients, which also hopefully you just recognize this is 0 no, that's something that's the formula is different. So basically what would happen is you would do 0.9 to the 5th, and you do 1 times 0.9 to the 5th plus 4 times 0.9 to the 4th and then you multiply that by 0.1 to the first, right? So as this goes down, this one starts going up, right? There was 0 of them there, now there's 1 of them there, plus 6, right? We're taking the coefficient from over here, 0.9 to the third times 0.1 squared, plus 4 is 0.9 squared. I'm going to have to delete my Pascal triangle. 0.9 squared, 0.1 to the third, plus what did I do wrong? 5. 1, 2, 3, 4, 5. Give me a second. Oh, I'm messing this up here. No, that's right. I see it was. I counted wrong. This is 0, 1, 2, 3, 4, 5. I should be using that one. So I got to erase my coefficients here. Should be 1, 5, 10. This would be 10. And then I go back to, let's see, 10, 5, 1. So then, okay, delete this again. The next one would be 5 times 0.9 to the first, 0.1 to the fourth. You can see how I'm just counting down on this one and counting up on this one. And the last one would be 1 times 0.1 to the fifth. Right? And so basically what this means is this is the So remember, this was success and this was fail, right? And so in this case, this is the probability of 5 success and 0 failures, right? So this is the probability that I hit all 5 targets, is 0.9 to the fifth, right? This is the probability of 4 success and 1 failures. This is the probability of 3 success and 1 failure. And this is the probability of 2 success and 1 failure. This is 3 success and 2 failures. This is 2 success and 3 failures, and so on and so forth, right? And so by looking at each term in this, you can see the probability of success, how many of these arrows are going to hit. And you could actually, then you have your probability distribution, right? If you want to know probability of 1 success, or start with 0, what's the probability of 0 successes? Well, you look over here at the last term, and it's 0.1 to the fifth power, right? So the probability of 0 is 0.1 to the fifth power. If you want to know the probability of 1 success, you're looking at this one, and you would end up with this, distribution of probabilities like we were talking about before. Okay, so hopefully you've already looked at binomial theorem. We're pretty comfortable with it already, but what I want you to notice is the way this is constructed is first by looking at the coefficient, right? These coefficients were determined by Pascal's triangle, but we don't always want to write out Pascal's triangle. So another way of looking at Pascal's triangle is this notation, n over r, which is basically n factorial over n minus r factorial times r factorial. So for in this specific example, our n was 5 because we're doing 5 arrows, and our r value is going to go from, r just starts at 0 and goes 0, 1, 2, 3, 4, right? Our r is going to increase, and so for example, if r was 1, we get 5. Well, so let's do 0 first. If r is 0, we get 5 factorial over n minus 0. Rewrite this. 5 factorial over 5 minus 0 factorial times 0 factorial. Remember, 0 factorial is just 1, so we really end up with 5 factorial over 5 factorial, which is 1. And that's the reason why we were using this coefficient, right? If you do the next one, you do 5 and then r is 1, you end up with 5 factorial over 5 minus 1 factorial times 1 factorial, which is 5 factorial over 4 factorial, which is just 5, right? Which is why you got this one. And if you do the next one, 5 to 2, right, you're going to get 10. And that's you can use the Pascal triangle, or you can use this. Your calculator can do this as well. But that's basically what the coefficients came from, right? So when we have this probability, what we're looking at is that function determining the coefficients, and then what I want you to notice is it's the probability of successes here to the nth power, right? So we're going to say p is success, so it's p to the n power, and then you end up subtracting R, right? And then it's whatever's here is the probability of 1 minus P, which is the probability of the thing not succeeding, and this is to the R power, right? So as this increase, we're subtracting 1, subtracting 2, this becomes 1, 2, 3, which it creates that, right? So this is how you determine that this probability distribution, right, is based on this formula here, and this is called the binomial distribution. And you also might see it like this, where it's and that's basically the same thing as this, except it just rewritten a little bit differently. Okay, this is some notation for probability for binomial theorem. Again, we're saying probably the P is going to denote success, and 1 minus P is then failure. Here's the probability distribution, right? Just like we just talked about, right? We had that up here. And R starts at 0 and goes to whatever n is. When we have this P of x equals R, we call this the binomial probability distribution. The expected value can be calculated by multiplying the number of things times P, the probability of success. That's a very easy one to calculate, right? Whatever n is, number of trials times the success. So for example, in the other example, we shot the arrow 5 times and the chance of success was 0.9. And so you just multiply those and you'll find out your expected value or your mean. And then a lot of times you'll see it written like this, where it says x is distributed as a binomial theorem of n and p. Again, n is the number of trials and p is the probability of success, right? So let's look at an example, right? We have 72% of union members in favor of a certain change to their conditions of employment. A random sample of 5 members is taken. So what we're going to do is x is distributed as the binomial theorem, n in this case is 5, because we are taking 5 members. The probability of success, the probability that they vote for this thing, is 0.72. Unless we're on the other side, then we're like, success is them not getting it, right? But in this case, it looks like that, which is going to look like, if we take our formula up there, right, we're going to have from 5R, remember R is going to go 0, 1, 2, 3, 4, 5. This is going to be 0.72 to the R times 1 minus 0.72, which is 0.28 to the n. 5, so n is 5 minus R, and this would give me my probability distribution, right? For example, if when R is 0, then I have 5 0 times 0.72 to the 0 times 0.28 to the 5, and that would give me 5 0 again is in Pascal's triangle. It is the 5th row and the 0th term, which is 1, and then this would just be 0, and this would be 0.28 to the 5th. And so this would actually represent R equals 0 success. So that would represent the probability that 0 people vote for this, right, is 0.28 to the 5th. Right? The probability that 0 people vote for it is 0.28 to the 5th, right? Then we could look at the actual questions here. The probability that 3 members are in favor of the change in conditions. In that case, we would want the probability, in this case, that x is 3, or maybe R is 3, in which case we would have 5 to 5, 3, don't draw the bar, and you got 0.72 to the R, which is in this case 3, times 0.28 to the 5 minus 3, which is 2, right? And then so this would give you the probability that exactly 3 members are in favor of the conditions, right? And you could work this out to figure out what that number is. Turns out you get 0.293, right? So about 29% chance that exactly 3 people get it. That exactly 3 people vote for it. Then you might want to know at least 3 members. That means 3, 4, 5 members, right? So what you would do is you'd figure out the probability of 3, and you'd add that to the probability when R is 4, and you'd add that to the probability that R is 5, right? So you'd calculate all 3 of those, and you'd add them together, and that would tell you the probability that at least 3 had it. If you want the expected number of members in the sample that are in favor of the change, remember the expected value is just n times p. So in this case, the expected value would be 5 times success is 0.72, and whatever that gives you, right? It would be your expected value. Okay, so that's binomial distribution. Now that you have that, you should understand better what this is here. You actually understand what the expected value is, and you can then, variance would just be plugging in some numbers. If they ask you for variance, you can just plug it into that, right? So next video we'll go over Poisson distribution.